last time I gave you a preview of the course. Today we're going to start looking at the actual analysis of these robot mechanisms. And the first thing we're going to look at today is the mobility of a mechanism, or alternatively known as the degrees of freedom of a mechanism. But before doing that, I just want to give you a demonstration of a simple little toy. It's a very nice toy, actually. It's a 5-degree of freedom robot mechanism. Okay. Now, I told you that a robot, from a mechanical point of view, can be just simply regarded as something that consists of joints and links. Okay, and the joints have motors attached to them. Okay, so when the motors turn, the joints turn, which causes the robot to move. Okay, so here you see a motor that activates the gripper. Okay, here's the elbow joint. It's an extremely slow robot. Okay, here it's moving in the base. Okay. Remember, it's a toy. Okay. Here's a shoulder joint. Okay. And then the wrist also turns. Not very well. Okay, there we go. Okay. You can think of it, as a very simple device. Just joints, links, with the joints driven by motors. Now, of course, if you look inside, and you can do this after class, you'll see that there's a lot going on inside. There are gear trains. There's all kinds of mechanical parts in there. Okay, we're not going to focus so much on the inside, what's going on in there. Okay, rather we're more concerned about, for example, here I'm basically moving the robot using my visual feedback. Okay, we want the robot to be smart enough, okay, to be able to know where to move the arm to pick up an object, place it somewhere else. Okay, those kind of tests. So we're looking at sort of a higher level capabilities. Okay, let me put this aside. Okay, so today we're going to be looking at mobility. Okay. And before I begin, just a quick note. Some of you have asked me why I don't use PowerPoint, why I'm using the board. So sort of my philosophy on this is, I can give you hundreds of pages of notes, PowerPoint slides. The point is that it doesn't help you. Okay, you have to make it your own. Okay, it's like that old story, right? Give a person a fish, he'll eat for one day. Teach that person how to fish, he eats for the rest of his life. It's the same way with notes, okay? So you can have tons of fancy notes, books, everything. If you don't make it yours, it's useless, okay? And I think doing this helps you to make this yours, okay? So that's what I'm going to do. Okay, so let's get down to business. So what is mobility? Well, most fundamental question you can ask, okay, in this course, at the beginning is, where is the robot? Okay? So we need to know where it is, where the hand is, where the base is. Okay? So here we're asking, well, can we describe the location of a robot in a precise, quantitative way? Okay? So let's ask a slightly simpler question. Okay? Let's pretend that the robot is now just a single rigid body. Okay? So I have a table here. Okay? And let me just put a coin on the table. Okay, and we're going to pretend it's a 500 won coin. Okay, so let's ask a question. Where's the coin? Where's the coin? In other words, can you give me a numerical description of the location of the coin? Okay. All right, so first thing you would do, right? So let's ask the question here. Where is the coin? Okay. All right. First thing to do is to pick a reference frame. Okay, so pick a reference frame. Okay, so let's pick one. Let me draw it here. Okay. And now we have to pick some points on the coin. Okay, so let's pick some points on the coin. So pick, let's see, how many points should we pick? Well, 1 probably won't do, right? 2, let's pick 3, okay? And we'll see later why we need to pick 3 points. Okay, so let's call these 3 points A, B, C on the coin. Okay, so here are my points. Here's A, here's B, and here's C. Okay. Okay, so now if I can describe the location of points A, B, and C, then I know the location of the coin. Okay. Now you'll see that why 1's clearly not enough. 2 is also not enough. Need 3. Okay. All right. So next, what we're going to do is, well, let's write down coordinates. Okay. So, and then next thing we're going to do is now let's think about what the constraints are. What the constraints are on A, B, and C. Okay. And because this coin is a rigid body, okay, you can't deform it. Okay, it's a rigid body. What that means is that the distance from A to B is fixed. The distance from B to C is fixed. The distance from A to C is always fixed. Okay. So let's write down those constraints in equation form. Okay, so the distance between point A and point B. Okay, so let's say that the coordinates for point A are XA and YA. Coordinates for point B are XB and YB. Okay, so the distance between A and B we can write as squared Okay, so there it is. Okay, and now this is going to be some fixed distance L1. Okay, so this is a fixed constant. Okay, we also have 2 more constraints. Okay, so distance between B and C is also going to be fixed. Let's just write it down. Okay, so this is going to be fixed to some constant L2. Okay, 1 more constraint. Distance between A and C. Okay, so this whole thing, square root is going to be some fixed distance L3. Okay? All right, so are there other constraints here? Well, this is all we need, okay, for the rigid body. All right, so let's now go back to the original question. How can we describe the location of the coin using coordinates? Okay, so originally we had 6 coordinates, right? xa, ya, xb, yb, xc, yc. Okay, but it turns out that because of these 3 constraints, those 6 coordinates are not independent. Okay? In other words, we have 3 equations, 1, 2, 3. Okay? And we have 6 parameters. 6, well, let's use the more colloquial unknowns. Okay? So, in math, you've seen this kind of reasoning quite frequently, right? 3 equations, 6 unknowns. So that means that in general, there's not a unique solution, right? In fact, we have 3 free parameters. Okay, so this is from 6 minus 3. Okay. Okay, so what this means is that if we fix the values for 3 coordinates, 3 of the 6, then the remaining 3 can be determined. Okay? All right, so that means there are 3 independent parameters. Okay? All right, so if we go back to the coin, let's now have a top-down view. So let's say that here's point A, here's point B, and let's say here's point C. So here's A, B, C. Okay? So if XA and YA, okay, and XB are given, okay, so XA is given, so this is given, XB is given. That means we know that the point B lies on this line somewhere. Okay? Then using these 3 constraint equations, okay, 1, 2, 3, we can figure out where the points B and C are. Okay? So this distance is L1, this distance is L2, L3. Okay? Using the constraint equations, we can figure out, can find the remaining coordinates, YB, XC, and YC. Okay? So that's what I mean by there being 3 independent parameters. Okay, so let's go back here. Actually, I wasn't being completely honest there. All right? Let me tell you why. Here's A. Okay, so I know B is on this line somewhere. Okay? And I said, that's the solution. Okay? But there's another solution. Okay? What is it? Well, turns out that's also a solution too. Okay. All right. So, given location of point A and given the x coordinate for point B, if I solve these three equations, then I can get this set, or I can get this set. Okay, so there are two solutions here. But if you think about this, what do I have to do to get to this? I have to flip the coin. Okay, I have to flip the coin. Pick it up off the table, flip it, and put it down. So this is a reflection. Okay, so we're not going to allow reflections. Okay, so won't allow reflections. Okay, so that eliminates this solution. Okay, so eliminates top solution. Okay, so we need three coordinates to describe the location of a coin on a table. Okay. Three independent coordinates. Okay, we used 6 before. Okay, 3 of which are independent, and the remaining 3 we obtain by solving the constraint equations. Okay. There's got to be a better way, right? Using fewer coordinates. Okay, so here's a better way. Okay, so let's just now draw the top-down view. So if I have a coin here, why not just attach a reference frame to the coin? Okay, so that's what I'm going to do. Let's attach a reference frame at the middle. Okay, and I'll just say that this vector to the origin of the coin has coordinates x, y, and the angle of the frame, this angle, let me call that phi. Okay, so now I can just use the coordinates x, y, phi, okay, to describe the position and orientation of this coin. Okay, describes the location of coin. Okay, so 3 coordinates. Okay, so this it's pretty straightforward. I probably didn't have to go through all this to convince you that this is a good way to do it, and it requires only 3 coordinates. Okay. But now, if we now consider rigid bodies in 3-dimensional space, okay, things become a little bit more interesting. So let's consider a rigid body in 3D space. Okay, so we learned a better way. Okay, so let's use this better way. So here's the body. So let's start things off by picking a frame. That's the sort of the universal or the fixed reference frame. And now let's attach a frame to the body. Okay. All right, so we want to describe the position and orientation of this body. Okay. So let's use that strategy again. So let's call this vector x, y, z. Okay. And now we need to describe the orientation of this frame. Okay. Now in the planar case, it was pretty easy. We just need one number, the angle, phi here. What do we do here? Okay, how many numbers do we need here? Okay, so orientation. What do we do here? Okay, well, first of all, how many coordinates do we need? Okay. Okay, so that's the more fundamental question to ask. Okay. Some of you might know the answer to this already. Okay. So how do we answer this question? Okay, so let's go back to basics. Okay, so let's do what we did for the coin. Okay, again, for this rigid body. Okay, so namely, let's go back and just pick 3 points. Okay, so A, B, C. Okay. And now let's write down the constraints, the relevant constraints. Okay. So it's the same constraint as before. Okay, so the constraints, okay, the distance from A to B is, well, let's write down the formula. So it's xa minus xb squared plus ya minus yb squared plus za minus zb squared. So the whole thing square root. So let me just do that. Okay, so this square root is some fixed distance L1. Okay, same constraint. Only difference now is that we have 3 coordinates, x, y, and z. Okay, so let's now go over here. Okay, the other constraints are the same. Okay, distance between B and C, okay, I won't write the detailed formula, is some fixed L2. And finally, the distance between A and C also is some fixed L3. Okay? All right, so let's go back to that counting game, okay? Number of equations, number of unknowns. Okay, so we have 3 equations. How many unknowns? 9 unknowns. Okay, so 9 minus 3. We have sort of 6 free parameters or independent parameters. Okay, so that means 6 coordinates describes the position and orientation of the rigid body. Okay, so 6 coordinates. So let's see, we used up 3 here, x, y, z. So that leaves 3 more. Okay, so that means orientation can be described using 3 coordinates. Okay. All right. Okay, so orientation requires 3 coordinates, okay, for a description. Okay, so I haven't told you yet how to choose those coordinates. There are many ways to do it, okay? But the important thing we know is that we need 3 to describe the orientation. Okay. Okay, any questions? All right. Now let's, so we talked about a rigid body, and I told you that a robot is, at some level, nothing more than a bunch of rigid bodies connected by joints. Okay, so now let's talk about the mobility of robots or robot mechanisms. Okay. All right, so we know what links are. Links are rigid bodies. What kind of joints do we find in a robot? Okay, so let's talk about that first. Some common joints. Okay, the one that we've seen the most so far is this rotating joint. Okay, it's called a revolute joint in the business. So use the letter R. Okay, so it rotates. Okay, some people call it a pin joint. Some people call it a hinge joint. We'll call it a revolute joint or R joint. Okay. Another common joint is something called the prismatic joint. Use the letter P for it. Okay, so it's so this is a linear joint, and its symbol I'm going to represent like that. Okay, so this allows for linear motion. Okay. All right. Another joint, something called a cylindrical joint. Okay, this you don't see quite as often. Okay. It's basically, symbolically, it looks like the revolute joint, but now we have both rotation about this axis, and we're going to also allow this joint to slide up and down. Okay, so in some sense, this is just connecting a R joint with a P joint together. Okay, so you can think of this as 2 separate R and P joints connected to form one joint. Okay. Another one is the universal joint. Okay. So this is just this is just 2 R joints connected orthogonally. Okay, so there's rotation that way, and there's also rotation about this joint. Okay, so as the figure indicates, this is just connecting 2 R joints in an orthogonal way. Okay. There's one other joint that's actually quite common, especially in closed chain parallel robots. It's called a spherical joint. Let's use the letter S. Okay. Now the spherical joint it's basically our shoulder joint. Okay. So it looks something like that. Okay, so we can sort of move our shoulder, and we can also do this. Okay. There are other joints, okay, but these are, I would say, sort of the basic ones. Okay. Now we can also talk about the mobility or degrees of freedom of a joint. Okay. Now I don't want to make a big meal out of this, so because it's intuitively pretty clear, I think, what we mean by the degrees of freedom of a joint. So the R joint, they have 1 degree of freedom. Okay, and let me just write the letter D, degrees of freedom as DOF. Okay, so if you specify 1 coordinate, that specifies the position of the joint. Okay. C and U joints, okay, have 2 DOF. Again, pretty clear. Okay. The S joint has 3 DOF. Okay. And if you think about it, the S joint, okay, what it's doing is it allows you to change the orientation. Okay. You see how my hand is moving? Okay. And we know that 3 coordinates are required to describe the orientation. Okay. So imagine a reference frame attached right here, a reference frame attached to the middle of this joint. Okay. And we want to describe the orientation of that frame. We need 3 coordinates. Okay, so we have 1 DOF joints, 2 DOF joints, 3 DOF joints. Okay, all right, so this should be pretty clear. Okay, now let's look at some basic mechanisms. Okay. Okay, so let's start off with the simplest one. Okay, so beginning of the class we asked that where's the coin, right? Pretending the coin was a robot. Okay. So let's look at planar robots for now. Okay. So let me just draw a link, 1 link. Oh, let me just draw maybe this way. Okay, 1 link. So how many degrees of freedom does it have? Well, obviously 3, right? So if you attach a frame here, for example, then let me draw the frame. Okay, sorry, let me reorient this link a little bit. Okay, so the frame would be that way. Okay, so we need coordinates x1, y1, and this angle phi 1. Okay, so we need 3 coordinates to describe the location, the position and orientation of this link. Okay. Now, if we had 2 rigid bodies, moving independently, obviously we need 3 plus 3, so 6 coordinates. Okay, so frame here, so this would be x2, y2. This angle would be phi 2. Okay. Now we're going to connect these 2 rigid bodies using a joint. Okay, so here we go. So now let's connect them using this R joint. Okay. All right. So how many coordinates do we need to describe the position and orientation of this robot or these 2 links? Okay. Well, let's see. We still need this. Okay. But now if you think about it, we don't really need, okay, x2, y2, and phi2 anymore. Rather, if we just know this angle, okay, so that angle, okay, so that's actually the angle at which this joint has been rotated. Okay, so call this theta 1. Then we know the position and orientation of this second link. Okay, so here we needed all this information to describe the position and orientation of the two independent, okay, links. Here, if they're connected by a joint, okay, we only need x1, y1, phi1, theta 1. Okay, so we need only 4 parameters here. Okay. And we can add another link, play this game. Okay, so if we do that, okay, how many parameters do we need? We need, right, y1, phi1, theta 1 is this angle, and we also need theta 2, which is the amount of rotation about that angle. Okay, so we need 5 parameters here. Okay. So you see the pattern here? Okay, so anytime you connect two bodies by a joint, what happens? The number of coordinates that are needed goes down by 2. Okay, so here it went down from 6 to 4. Okay, now we have 2 joints, so it went from 3, 3, 3, 9 to 5. Okay, so every time you see a joint connecting 2 bodies, that eliminates 2 coordinates. Okay, all right, so this is a useful observation. Now, if we consider a 2 degree of freedom joint, okay, so let's just draw a robot. And this time we have a revolute joint and a prismatic joint. Okay, so it's something like that, kind of strange. Okay, so here we have revolute joint, and we also have a sliding P joint here. Okay, so we're going to regard this as a single 2DOF RP joint. Okay, so how many parameters are needed here? Well, as before, we need x1, y1. We also need the angle, phi1. But now if we know the values of the joint angles R, so call this theta 1, and P, this P joint, call it, say, D1. Okay, then we need 5 coordinates, right? x1, y1, phi1, theta 1, D1. Okay, so 5 coordinates. So without this joint, we need 6. If we connect these 2 bodies using a single 2DOF joint, it goes from 6 to 5. Okay? If we added another link out here using a 2 degree of freedom joint, you see that it goes from 9 to 7.